So, we're back to stratospheric chemistry this week. So Hugh Coe tells me this was the last slide he got up to last time. Is that right? Can you all recall? So just by way of recapping where you'd got up to. Do you remember the Chapman cycle? So this should be something that's very familiar to you all. And it's the cycle of odd oxygen chemistry that happens up in the stratosphere that describes the amount of ozone and oxygen atoms and the proportion of each and the loss processes and production processes of ozone in the stratosphere. So very simply put, oxygen photolyzes, molecular oxygen photolyzes to produce atomic oxygen. Atomic oxygen itself can react with molecular oxygen in a three-body reaction to form ozone. So that's the formation chain. Ozone can then photolyze to re-release molecular oxygen and atomic oxygen. Oxygen can react with ozone to produce molecular oxygen, and then recombination in a three-body reaction of atomic oxygen can lead to molecular oxygen production. So you've got a whole bunch of very fast odd oxygen chemistry, production of odd oxygen, and then loss of odd oxygen. So reactions 2 and 3 govern the ratio. So they don't create or destroy odd oxygen or ozone. They just recycle it and turn it from either ozone to atomic oxygen. The ozone production is limited. The ozone production and loss is limited by reactions 1 and 4. So the deozone by dt is twice the rate of photolysis of molecular oxygen minus recombination rate of ozone plus atomic oxygen. The ratio of the two odd oxygen species, that's atomic oxygen and ozone, is just determined by the production divided by K2. And odd oxygen atoms are only important above 50 kilometres. So that tells you that the main odd oxygen species in the stratosphere is ozone, which we all know. And if you do the calculations according to the Chapman cycle, you get this dotted line here. You get these lines here. But the observations are always smaller. So you're missing an ozone sink. So we're going to start today's lecture by considering what the ozone sinks can be and why the ozone sinks happen and when they happen. So this should be really pretty much recap for you, but some of the details on it are important to actually capture because they're, number one, you might find them in the exam, but number two, they are the things that really control the ozone in the stratosphere. They're not the ones that just determine the natural cycle. So they consider the human perturbations to ozone in the stratosphere. So what do we think happens to the ozone that's not in the Chapman cycle? So who can give us some guesses about what the rest of this lecture is about? Why is ozone destroyed in the stratosphere? CFCs is one thing. Okay, so CFCs, we'll come on to that as the last of the cycle. So they're chlorinated compounds, but it's not just chlorinated, it's generally halogenated compounds, so it can be bromo or fluoro compounds as well. But what other cycles? Well, there are three sets of cycles that perturb the ozone in the stratosphere that are outside the natural Chapman cycle. The first of these is the Hox cycle. So what's Hox? Do you know what Hox are? Hox is just the sum of the hydroxyl radical and the hydroperoxy radical. So what's the hydroperoxy radical? The hydroperoxy radical is this compound here, HO2. So in order to get rid of ozone, you can do two things. Either you've got to have something that is much, much more abundant than the ozone, or something that's regenerated. What do we call something that's regenerated in a chemical reaction? Catalyst, but in the case of these reactions, they're autocatalysts. So they're created actually within the chemical cycle. So they're not inert things that are reacted upon, they're regenerated and created. So they're autocatalytic cycles. So the first of the autocatalytic cycles was discovered in around 1950, or it was suggested that these OH and HO2 species, these Hox, could be continually cycled and destroy ozone. So the hydroxyl radical can react with ozone to produce the hydroperoxy radical and oxygen. The hydroperoxy radical itself can react with atomic oxygen, which we saw from the Chapman cycle is produced from the photolysis of molecular oxygen, and regenerate the hydroxyl radical. So if you add these two reactions together, this says that atomic oxygen plus ozone leads to molecular oxygen plus molecular oxygen. So where do we get the OH from? So what do you need to make OH? Well, you need light, because you need to photolyse ozone to produce O singlet D. But O singlet D, most of it is stabilised. So if you remember from the gas kinetics lecture, the last but one lecture we had in the atmospheric chemistry part, most of the O singlet D is stabilised, the hot O singlet D is stabilised to step to the ground state oxygen atoms. And only the little fraction that's left is allowed to react with either water to produce OH, or it can react with methane to produce the methyl radical plus OH. But the stratosphere is dry. Why is the stratosphere dry? Does anyone know? Pressure's low, number one. But there's also the tropopause, the boundary between the troposphere, where most of the water vapour lives. Yep, so there's an inversion, a temperature inversion, which stops the ready mixing between the troposphere and the stratosphere. And most of the water vapour is evaporated from the surface. So most of the water vapour is in the troposphere. So the stratosphere is dry. And so this O singlet D plus water vapour, which is the main reaction to produce OH, can't happen very efficiently because you haven't got much water vapour. So there isn't much OH in the stratosphere. Where there's methane to react with, that can also produce it, but there's not as much methane. There's nowhere near as much methane as there is water vapour. So not much water vapour, and so not much OH, so not much destruction of ozone from OH. So the Hox cycle happens, but it's not very efficient because you haven't got much hydroxyl radical. So what other cycles are there? We've mentioned CFCs, so we'll come on to that afterwards. What other cycles are there that can destroy ozone? You've got the Hox cycle. The next cycle is the NOx cycle. Okay? So what we've got, if you remember it, Hox, NOx, and when we come to CFCs, it's clocks. So Hox, NOx and clocks are the three additional cycles on top of the Chapman cycle. So 1950 was the postulation that the Hox cycle could be involved in ozone destruction. In 1970, there was this idea that bacterial nitrous oxide can catalytically destroy the ozone. So how does this happen? If you look, we know from the gas kinetics lectures that we've had that NO can react with ozone. It's one of the reactions in the troposphere that leads to the photostationary state of NOx. So NO can react with ozone to produce NO2 and oxygen. NO2 itself can react with atomic oxygen to produce the NO again. So again, the net sum of those two reactions is that oxygen atoms plus ozone lead to molecular oxygen. So where does the NO come from? We've just said that bacterial N2O, what other sources of N2O are there? Any idea where N2O happens in the atmosphere and why? N2O can be formed from lightning and from bacterial emissions. So where does lightning happen? Lightning happens in the atmosphere itself, wherever there are clouds that are sufficiently vigorous to produce the electric discharge. And then the bacterial emission happens at the surface. Now N2O itself photolyzes to produce nitrogen. And 90% of it produces just nitrogen. So it means there's not very much NOx that's formed from N2O. So what's left, the other 10%, can react with hot oxygen to produce NO. And about 58% of it does this, and another 42% of it just goes to N2. So overall, about 6%, so 58% of 10%, so about 6% of N2O can lead to this cycle. So again, the NOx cycle isn't very efficient. So the Hox cycle isn't very efficient because there's not much water vapour up there. And the NOx cycle isn't very efficient because most of the N2O just produces nitrogen, which is inert and doesn't produce NO. So we've got the Hox cycle, not very efficient, but it happens. The NOx cycle, not very efficient, but it happens. So first of all, you've got the Chapman cycle, which is the natural cycle. Then you've got the Hox cycle. Then you've got the NOx cycle. Now, we know that N2O has gone up through the post-industrial era. Okay? Now, that constitutes the ground source of N2O. And you've got to get the N2O up into the stratosphere for it to act as an ozone destroyer. Because it's going up, and there are measurements of N2O going up in the stratosphere itself, not just at the ground, we know that what you do at the surface can affect what's in the stratosphere. Because N2O doesn't photolise efficiently at tropospheric wavelengths, so it lives for a very, very long time. So it becomes very, very well mixed in the atmosphere, and so gets up to the tropopause, and went through the very slow mixing from tropospheric folds, it can reach the stratosphere. So in the post-industrial era, we've managed to increase the amount of N2O, mainly from increases in agriculture to feed the population that's been growing in the post-industrial era, which increases the well-mixed concentration in the troposphere, which mixes into the stratosphere slowly, and there it can photolise because the high-energy photons are present in the stratosphere that allow N2O to photolise. So although the Hox and Knox cycles are inefficient, they both happen and will add to ozone destruction more than you would see if you just predicted the ozone concentration from the Chapman cycle. So this study, which was in the early 1970s, was made by a guy, Paul Crutzen, who later on had a big role to play in the stratospheric ozone depletion from CFCs. But he postulated that the fertilising of crops, which is needed for the increasing population to get efficient food production to feed the number of people in an increasing industrial anthropogenic era. The N2O has a long lifetime, it can reach the stratosphere, it increases the stratospheric NOx, and the increase in NOx decreases the steady state ozone. So that was the first indication, it was the first time that we understood that human activity could actually affect the stratosphere. But then came the really big bombshell, which was the clock cycle. So we understood already from the NOx cycle that human activity at the ground could affect the stratosphere. But there were still these ozone depletion observations to explain that couldn't be explained just by the Hox and the Knox cycle. And then it was postulated in 1974 that some really, really successful chemical compounds that were just made by anthropogenic sources, so they weren't natural. There were no CFCs before men made them. And DuPont built a huge, DuPont were the manufacturers of most of these. And what were CFCs for? Why are they good? What's so special about CFCs? Sorry, there were loads of voices. There were air conditioning. So they're chemically inert. Why are they good at air conditioning? Their heat capacity and their phase state at low temperatures, they're still liquids at low temperatures, they're covalent liquids. They can resist high pressures, they can resist high temperatures as well because they're inert. And they are extremely stable. So these stable things across a very, very wide range of pressure and temperature meant that these were fantastic engineering fluids. And DuPont made billions from manufacturing CFCs. So CFCs are made from carbon, chlorine, fluorine, bromine, etc., etc. And they're numbered according to the number of carbon atoms, the number of fluorine atoms, and the number of chlorine atoms. So CFC 11, the rule is CFC 11, add 90 to it, that means 101. The first number is the number of carbons, the last number is the number of fluorines, and everything else is chlorine. So it's C, it's F, and then it's Cl3, because carbon has to have 4 molecule, 4 atoms associated with it. So CFC11 is trichlorofluoromethane. But the upshot of this is that these CFCs are very stable at the ground, but they're not stable up in the stratosphere. So why aren't they stable in the stratosphere? Because they photonize. Because that's where all the energy is. So all these photons of high energy can actually make the CFCs unstable in the stratosphere, even if they're stable at the ground. So what happens is that you release chlorine atoms. The chlorine atoms can react with the ozone directly to form ClO. ClO can react with atomic oxygen to form the chlorine atoms again. And the net of this is the same as the net of the other cycles. So oxygen atoms plus ozone plus gives you molecular oxygen. The thing that makes this an extremely efficient cycle is that every single molecule, every single atom of chlorine can destroy about 100,000 molecules of ozone. So if this happens, this goes round 100,000 times, every time destroying an ozone molecule. So whenever there's photolysis of one CFC molecule to produce chlorine, you can destroy 100,000 molecules of ozone. So unlike the HOX and the NOx cycle, the CLOX cycle is really, really efficient. So you don't need much CFC to deplete a lot of ozone. So just a small amount of CFC can deplete a lot of ozone. So if you look at the usage of CFCs, this was in the 1970s. This was when it was discovered that the CLOX cycle was effective. Propellants. What does it mean by propellants? So the main use of CFCs in the 1970s was not for refrigerants. What was it for? No, not rockets. Spray cans. So it's for deodorants and paints. Yeah? Propellants. So it propels the product out of a can. So spray cans. 3/4, or nearly 3/4 of CFCs were used in spray cans. What do we use now in spray cans? Do you know? Well, we use things that are not as safe. We use some HFCs, but sometimes we use things like butane. And these can be flammable. But it's thought now that it's better risking flammable propellants rather than damaging the ozone hole, damaging the ozone layer. So they've replaced the very, very good engineering fluids that DuPont invented, and they said, well, hang on, we just can't damage the ozone layer. So they replaced it with things that aren't as good as the CFCs, so that we actually stop damaging the ozone layer. So the spray can ban, which had all of these propellants, came in the mid-70s. And there were refrigerants, cleaning agents. So for cleaning agents, you know dry cleaning, when you take your clothes that don't like being exposed to detergents and water, they all used to use things like carbon tetrachloride, CCl4. And so those cleaning agents, refrigerants, blowing agents, and other usage was banned under the Montreal Protocol in the late 80s, early. When was the Montreal Protocol? Can anyone remember?
1991.
Or two, I can't remember. Yeah. See, I remember the discussions in 1991. I can't remember if it came in 92. But anyway, so that happened in the 90s. And you can see that the thousands of tons, nearly sort of high fractions of 1 million tons every year was being produced, was stopped over a period of about 5 years. Have we completely stopped CFC production now?
Some countries.
There's some in China. It's coming down. Oh, there is still. We know this because we've flown some planes across and we've measured CFCs over China. Or that's coming in the outflow from China. But much, much more from other developing countries. Because they're such good fluids, and they are really, really good. I remember I did an engineering degree, and I did this in the 1980s, and all of our product design in all of our courses was based around choosing different CFCs. And this was fantastic. Oh yeah, this is a great CFC for this job, or this is a great CFC for this job. And you just look at the different pressure, temperature regimes that you could choose these fluids. And they were accepted practice to use CFCs. So, their residence time in the atmosphere outside the stratosphere is between 50 and 300 years. So this tells you that they're mixed right around the globe really easily. How long does it take to mix something into the atmosphere? Into the troposphere? How long will it take? What sort of lifetime would you need in order for something to be mixed well in the troposphere around the globe? It's of the order of years, a few number of years, and then you can become well mixed. They have a huge residence time, 50 to 300 years. So CFCs that are already in the atmosphere, they're still there. And they'll be there for a long, long time. And that means that they can still mix up into the stratosphere. How do we measure CFCs? It's really difficult. Why is it difficult? Because it's inert. So you can't use a reactant to detect it. So there's a smart guy, Jim Lovelock, that designed... Do you know what Jim Lovelock is famous for other than designing this? Does anyone know anything about Jim Lovelock? Has anyone heard of the Gaia theory? I hate plants. Has anyone heard of the Gaia theory? The Gaia theory is that the Earth and humans and all life developed and evolved together. And that if the Earth becomes unsustainable for life, or if life and Earth become unsustainable for each other, then the homeostasis of the planet actually breaks down. Now, it's a very clever theory. It doesn't necessarily... it's not necessarily as rigorous as it could be. But have a look for Jim Lovelock, or James Lovelock. And look up the Gaia theory. It's quite an interesting theory. And it was something that was used as a really useful tool to try to understand the relationships in climate change. It's not absolutely perfect theory, but it's quite an interesting one. Anyway, that's an aside. Jim Lovelock built and invented the electron capture detector. So if you use a gas chromatography column and you put the gas through the column up against a radioactive foil that emits beta particles, then there'll be amount of current from this foil reaching the cathode. And so that will develop a current between the cathode and the anode when these two are connected up. If a gas absorbs some electrons, then it reduces the amount of current. And the reduction in the current is proportional to the amount of gas. So the electron capture detector was able to detect these very, very small concentrations of CFCs that came out of a gas chromatography column. And look at that last statement there. Oh. The presence of these compounds constitutes no conceivable hazard. Okay? So this was before anyone postulated the clock cycle. So they thought that DuPont chemicals were completely inert and presented no conceivable hazard. And this was just in 1973 when Jim Lovelock measured these compounds in the ocean and the atmosphere using his newly invented detector. And in 1974, the conceivable hazard was discovered. So it only lasted for 1 year before it was found that these were really, really dangerous. But it was a bit too late by then, because there was always this inexorable rise of CFCs in the atmosphere. So even though it was discovered in 1974 that there was a problem, the CFCs, because only the propellants were banned, there was still a huge production that increased the concentration of CFCs in the atmosphere right through from the 1970s to the mid-1990s. It started falling off. If you see here, it starts slowing down after the Montreal Protocol. So the CFCs, because they live for about 50 to 300 years, and we started putting them in the 1930s, they were increasing continually, and they weren't going to stop as it rose in the atmosphere. Now, because these guys in 1974 realised that the CFCs were photolised in the stratosphere, they made predictions of the amount of ozone loss. So if you look here, these are the concentrations, because it's very slowly transported from the troposphere into the stratosphere. These are the concentrations that were predicted as a function of altitude. So the different CFCs have different concentrations, and they're predicted to be living for longer or shorter lifetimes in the stratosphere. So why do they fall off in concentration with height? So what's happening to the CFCs when they get transported into the stratosphere? So they get mixed up through the tropopause, and you see the concentration is the same, because they're well mixed in the troposphere. They get moved across the tropopause through slow mixing, through tropospheric folds and trop exchange, and then their concentrations fall as a function of height. Why do they fall off? Because the intensity of sunlight of higher energies increases with height. So they're all photolised at different rates with the high energy photons. So you can predict what the profiles look like in the stratosphere from the penetration depth of the different wavelengths of light. So remembering back to the photolysis discussion in the earlier lectures, the higher energy wavelengths penetrate less through the atmosphere because they are absorbed most quickly by most molecules. So you get a profile of UV through the stratosphere, and you get a profile of the compounds that absorb through the stratosphere. What was also observed at different locations with different concentrations. Now, I said earlier that the CFCs and the HCFCs are well mixed. If they're well mixed and you measure them at different places at different concentrations, what does that mean? Does that mean that they're not well mixed and I'm wrong? There are sources that are contributing more at some locations than other locations. So the difference in the concentrations can tell you where the CFCs are being emitted. So whilst when they get into the atmosphere they become well mixed because they live for so long, if you've got a source here, then you're going to measure more concentration here than you'll measure here. Eventually it becomes well mixed, but if you continue pumping sources, you still see more concentration closer to the source. So this is what atmospheric models do. They relate the emission sources, the meteorology and the concentrations by how close something is to the source, how reactive they are, how well mixed it becomes because of the meteorology. And this is an indication of the differences in different regions producing different amounts of these HCFCs. So what we have are the sources of the ozone-destroying compounds, their lack of reactivity and their persistence and their increase through the atmosphere, the transport. So this was in the lecture that Hugh presented a couple of weeks ago. Do you recall the Breuer-Dobson circulation that gets these compounds into the stratosphere, that then leads to them being trapped in the polar vortex, penetration of UV radiation, and the release of the chlorine. The chlorine plus the molecular ozone, the ozone leads to ClO. The ClO can react again with atomic oxygen to reform your Cl, and you net ozone destroy about 100,000 molecules for every single release of chlorine. So that's just a summary. But now we've got the Hock cycle, we've got a Knox cycle, we've got a Clock cycle, and we've got the Chapman cycle. These all control the ozone and the concentration of O, or the ratio of the concentrations of O to ozone, to a varying degree, depending upon how much of each cycle is happening. But not only do they individually control the ozone concentration, but they also couple. So the cycles, the Hock cycle, Knox cycle, Clock cycle, and the Chapman cycle are all coupled. So we've got production terms, we've got loss terms, and we've got recycling terms, so propagation. Excuse me. So the Hock cycle is coupled to the Knox cycle through the reaction of OH plus NO2 to form nitric acid. The Clock cycle can lead, well, losses, sorry, this is not coupling. The chlorine can react with methane to produce hydrochloric acid. Both of these compounds are very soluble and can be removed by exchange with the troposphere and precipitation. But you can couple the Clocks and the Knox cycle by the reaction of ClO plus NO2, and the Hocks and the Clock cycle by the reaction of HO2 with ClO, and create these reservoir species. Now the reservoir species lock away your reactive chlorine and your reactive NOx. So the reservoir species are things that temporarily slow down the ozone production, ozone destruction. And if you look at this, between 90 and 99% of the radicals that destroy the ozone are locked up in the reservoirs. So they're just waiting there. They are potential ozone destruction waiting to happen. But it doesn't happen all of a sudden. So it stops the continuous destruction of ozone and waits until the conditions are right to lead to ozone destruction events. So when does ozone destruction happen? Okay, yeah. So polar spring. So what happens for the rest of the time is things cycle around and get locked up in these reservoirs, just waiting for the conditions to be right. But these reservoirs actually interchange with other species, as we'll see in a bit. But they get locked up in HOCl and ClNO2, these cross-reaction products of the different cycles, about 90 to 98% or 99%. So if we didn't have the reservoirs, we'd eat up all the ozone. All the time. So there would be no ozone up there, because these CFCs are so efficient that 100,000 molecules of ozone will be destroyed for every Cl, and they just run around these cycles, and you'd have nothing to stop the ozone being completely destroyed. So we're quite lucky that there's these locking up of the two cycles. So the HO2 can react with ClO to give you the HOCl, which photolyzes slowly back to the Cl. So a lot of your ClO is locked up in HOCl, but also the ClO can react with the NO2 and lock up your ClO-NO2, which again photolyzes quite slowly back to Cl. So the green arrows are really, really fast, and the orange arrows are quite slow, but they form these large reservoirs of the reactive chlorine. So these are fairly unreactive, these are very reactive. And then the Cl could react with methane to produce this, and that would lose Cl from the system. It would go down to the troposphere, and because it's soluble, can be removed. So if we got this, do we understand the basic, grasp the basic reasons why we don't have the same amount of ozone that you'd predict from the Chapman cycle? And that not only do we have these different cycles participating, but these cycles interact and lock up the reactive species in less reactive reservoirs. That's the key message to remember. And there can be some removal because of the reaction of the chlorine with methane. Right. Got a bit of an exercise for you. Will you all just spend until 3 o'clock trying to run through these? So the next 10 minutes, don't look at the next slide. Just see if you can work through these. You should be able to run through these yourself. The answers are on the next slide. If you want to cheat, you can. But if you just spend 10 minutes thinking about it, and then I'll explain why these are useful sorts of exercises to go through. Okay? 10 minutes of just running through those.
So you're comfortable with that sort of an exercise? Is everybody happy that they'll be able to do that sort of an exercise if they were asked it in an exam? I'll just run through some of the general principles. If you look at this cycle here, AB plus C in a substitution reaction is effectively just leading to a change of product, so you've got AC plus B. AC might photolyze to produce atomic C and atomic A. Atomic A could recombine in a three-body reaction to give you AB plus regenerating the third body. And the sum of those is 0. So no net sum of any of the species. Can anybody tell me what the rate of change of AB is? So what's the source of AB? So D of AB by dt equals the production of AB minus the loss of AB. Okay? What is the P of AB? What's the production rate of AB? Sorry? So it's K3 times A times B times N. Okay? What's the loss? So AB is only produced in this reaction. What's the loss rate of AB? Is just so the rate of change of AB is dependent upon the concentration of A, the concentration of B, it's pressure dependent, and it's also dependent upon the concentration of C. The loss rate itself is dependent upon its own concentration, AB, as well. So the rates of change of all of those species are just given by the examination of the equations on the previous slide. If this is in steady state, what does it mean? Means that's 0. Means there's no change in AB with time. If there's no change in AB with time, it means that PAB equals loss AB. If the production rate was greater, then it wouldn't be 0. If the loss rate was greater, then it'd be less than 0. So K3 A B M equals K1 AB C. So AB is K3 A B M divided by K1C. Does everyone follow that? It's exactly the same as we've done for the steady state expressions there. And all we've done is use these steady state expressions to back substitute. So ClO equals K4NO2, and so we just back substitute that into here, etc. And so all we're doing is using these steady state expressions to back substitute to derive the expression for d-ozone by dt. And it says that d-ozone by dt is just dependent upon the ClO concentrations and the O concentration. So it's not dependent upon any other concentrations, which allows you to do the calculation. If you're given the ClO concentration and the O concentration, it allows you to say how many molecules per centimetre cube per second of ozone are destroyed at the height. So at 15 kilometres, so this is, 40 kilometres, where you're given the O concentration and the ClO concentration, you can calculate the d-ozone by dt. So you need to be comfortable with rearranging the different cycles, if you're given the expressions, to the rate constants, to the steady state expressions, to then be able to conduct those sorts of calculations. So these sorts of things, what you've done in previous years? Yeah? So it should be no problem whatsoever in rolling out anything associated with stratospheric chemistry. It could be any combination of those sorts of expressions, any cycle, the Chapman cycle, Hock cycle, Knox cycle, Clock cycle, but then you need to be able to manipulate those. But you also need to understand and interpret them. So what does it actually mean? And why are those concentrations what they are? So if you look at this vertical profile of the ozone of the concentrations of the different participating species in the atmosphere, here's a pressure scale, this is an altitude scale, and this is the loss rate. So it's the total loss rate of the odd oxygen species, that's atomic oxygen plus ozone. You can see total loss through here. The production rate. So you've got the production and the loss, the different amount through the Knox cycle. Here's a Brock cycle. So what do you think the Brock cycle is? It's exactly the same as the Clock cycle, but with bromine species instead of chlorine. Exactly the same. It's with the odd bromine, so you end up with bromine as the atomic species instead of chlorine. And the various contributions. And because of these different slopes and profiles, you can see that the Hock cycle is most important here, the Knox cycle is most important here, the Clock cycles are most important here, and the Hock cycles again are most important here, because of the different participation. Okay, so the interpretation of this is dependent, because if you look in the question, you were told what the Clock species and the odd oxygen species concentration were, which allowed you to get the ozone destruction rates.
So it's these sorts of profiles that are necessary to tell you what the concentrations are, to tell you where the different cycles have different levels of importance. So what happened then? So just a bit of a history lesson to wrap up with ozone destruction. You can see late 60s, early 80s, late 80s, we've got this continually reducing amount of ozone above Switzerland. So this was a stratospheric profile, not taken over the polar ozone layer, but this was above Switzerland. And you can see that this is the sort of trend, minus 2.9% per decade. So the ozone, the stratospheric ozone, was being depleted in a worldwide sense, not just over the polar vortex. This was reported in 1994. But it wasn't the gradual decrease globally in ozone that made the headlines, that let us know that we needed to do something about it. It was all driven by an observation in the mid-1980s of really, really severe ozone depletion. So whereas this profile showed that there was a reduction of a few tens of percent or between the late 60s and the late 80s, the ozone depletion over the South Pole was much, much more dramatic. So the way they found it was by letting off balloons. So these balloons going right through the atmosphere with sondes to measure the ozone concentration. So do you remember what a Dobson unit is? So what's one Dobson?
1 millimeter is equal to the pressure of...
One Dobson unit is 100th of a millimetre. Okay? So if you squashed all of the ozone in one Dobson unit column down to the surface, it'd be 100th of a millimetre thick. So through the atmosphere, normally about 300 Dobson units, you've got about 3 millimetres worth of ozone if you squashed it all down. So it's not very much. So from about 300 Dobson units, the monthly average was shown to decline down to around 100. So from 3 millimetres to 1 millimetre. So it doesn't sound as though there's a lot of ozone there, but the change was huge. And that change, these here, were averages for October. But it's not the average concentrations that were the important thing. It was these complete depletion events where you had the runaway destruction of ozone that meant that there was zero ozone at certain parts of the atmosphere. And you can see here, at the South Pole Station, you'd actually gone down at 15 to 20 kilometres, you'd gone down to zero ozone in the atmosphere. So this was 96 Dobson units averaged throughout the whole column, instead of about 260. And here, these satellite observations I'm lying. Are these satellite observations? I'm not going to give myself a clue. Right. Can somebody go away and find out whether these are satellite observations or whether these were model simulations? I believe these are satellite observations of the ozone hole appearance throughout October from 1980 through to 1991. And you can see that the strength of the ozone depletion is different from year to year. But nonetheless, every single year there is a very, very large depletion in ozone. Yes, these were satellite observations. It's all right, I remember now. These are total ozone column measurements. And so because they vary from year to year, the measurements of the average size of the ozone hole can be recorded to get this sort of a trend out. Now that is in millions of square kilometres. So you're talking 20 million square kilometre ozone holes. That's quite a lot. So that's over the South Pole. And the minimum ozone in Dobson units was shown over roughly the same period to run down to almost zero. So what do we understand about the polar vortex? Why does this happen around polar spring? We've got the locking up of the air in the polar vortex and isolation from the other latitudes. And it becomes very, very cold. So there's thermal radiation to space during polar winter. There's no sunlight to heat it up. And so this vortex strengthens. So with the strengthening vortex, you've got all of these species being locked up into the same air mass. And it gets cold. So during the polar winter, you get down to about minus 95 centigrade. Now we've already shown how you've got this coupling of the Knox cycle and the clock cycle to form CnONO2 reservoir, and Hox cycle and the clock cycle to form the HOCl reservoir. Because 90 to 95 or 98% of the reactive chlorine is locked up, you can't get this runaway ozone destruction to destroy all of the ozone. But in the winter, because the temperatures drop so fast, you end up with the formation of these very particular sorts of clouds, the polar stratospheric clouds. And these are the ones, they look like that. So they're sort of luminescent, high-level stratospheric clouds. And they're made of ice. But special forms of ice. So where's a... Yeah, that's good. It's in the wrong place, this slide. Oh, no, it's not. But yes, so during the polar winter, you end up with these polar stratospheric clouds in layers between 15 and 20 kilometres up. So if you recall, the ozone is completely depleted between 15 and 20 kilometres that corresponds to the height at which the temperature is just right for polar stratospheric clouds. And the clever part of the linkage between the chemistry and the finding of the ozone depletion from observations was the understanding of the role of the polar stratospheric clouds. Because the gas phase can't explain the ozone destruction, it was thought that there must be something happening on the surfaces of these clouds. If it gets very, very cold, below 188 Kelvin, you get crystals of pure ice. And so these pure ice crystals don't have any fancy chemistry happening on them. But if you're above 188, so between about 190 and 200 Kelvin, where the temperature's just right,
you can form nitric acid trihydrate. And these NAC crystals, which are formed in the ice, so nitric acid trihydrate is a solid, okay? So they're crystals, the clouds, the polar stratospheric clouds that are formed between 190 and 200 Kelvin, thermodynamically can be shown that they comprise nitric acid and water vapour growing on small sulfuric acid particles. And these are NAT, the nitric acid trihydrate. Now it turns out that 90% of the polar stratospheric clouds are this sort of a cloud because they're formed at these warmer temperatures. And what happens on these crystals of nitric acid trihydrate, you can have the following reactions. So we know that HCl is formed from the reaction of methane and chlorine. That can react with the chlorine nitrate, the reservoir species, to release nitric acid and Cl2. The chlorine nitrate can also react with water on these nitric acid trihydrate particles to form nitric acid and HOCl. The hydrochloric acid can also react with the reservoir species HOCl to give you water and Cl2. And the N2O5 can react to give you N2O5 that's formed from... Sorry, I haven't been through the N2O5 cycle. You don't need to know too much about the N2O5 cycle. It's just that you release. Okay, I will go back because I'll cover N2O5 in the next tropospheric lecture. What's N2O5 made from? Do we know? NO2 plus NO3. Do we know what NO3 is? The nitrate radical. But this is a thermal equilibrium, so this unimolecular decomposition can re-release NO3. So N2O5, dinitrogen pentoxide, is formed from NO2 plus NO3. NO3 is formed from the reaction of NO2 plus ozone, and the N2O5 can decompose again if the temperature is hot enough to NO3 plus NO2. But the N2O5 itself can react on these polar stratospheric clouds to form nitric acid and ClONO. So that's not a typo. It's not ClONO2, it's ClONO. And these are all active chlorine species, and these are inactive. So what happens? Well, nothing. Because all of these gas phase species are still in the dark. So the reactions have happened on the surface of the polar stratospheric clouds and released these active chlorine gases. These active chlorine gases wait until the sun comes out. So everything's trapped in the reservoir species normally, so you can't get runaway ozone destruction. Then everything gets locked up in the polar vortex. Everything gets colder. The polar stratospheric clouds form. The reservoir species react on the surface of these clouds and release these gases. And then nothing happens until the sun comes out. When the sun comes out, all of the high energy photons that weren't there when these reactive chlorine gases were made start to break down the active chlorine and form the clock cycle.
And so this runaway ozone depletion can happen because your reservoirs have been turned into the active species. So you get these depletion events when the sun comes up, breaks down the polar vortex, and gives you enough solar radiation to start the chemical reactions going. So just in summary, the meteorology, the formation of the polar vortex at low temperatures, isolates the air packets, forms PSCs, heterogeneous reactions on the surface of the PSCs, lights come on, the ozone loss by the autocatalytic reaction cycles. Okay, so that's just more observations. Here's observations not just of the ozone hole, but they're observations of the CLO species, the ozone species, nitric acid, and the ClO, showing the correspondence between the different species playing a role in the chemistry and the ozone destruction itself. Right, okay, so these are just illustrations of the timeline, just over reinforcing and emphasising what I've said. So you're all comfortable with the whole of the ozone destruction story in the stratosphere. So does ozone destruction happen in the Arctic atmosphere? If it does, why? If it doesn't, why? There isn't a landmass, so the Arctic is warmer. So you haven't got this big ice block, this ice-covered landmass. You've also got planetary waves that mean it's harder for a vortex to form. So you don't get the locking and the protection of all the chemical species in the Arctic to the same degree that you have in the Antarctic. And so you do get ozone depletion, but you don't get them to the same degree because you haven't got the locking away of the air in the Arctic from the air surrounding it. So your planetary waves are there because you've got a lot more land, you've got a lot more continental shelf. The planetary waves break down the vortex, stop it from forming very, very effectively. You don't really get the polar stratospheric clouds because you don't get the thermal cooling in the same way in the Arctic winter. So you get some depletion, but if you look at the level of depletion, you're going from about 4.8 millimetres to about 3.4 millimetres of ozone at the ground. So 480 to about 340 Dobson units here. Right. Now, we've got a choice. We can start moving from the stratosphere and dropping down to the troposphere, if that's what you want to do. I think we've got plenty of time left, but what I'd like to do is invite questions about the stratosphere, because I'm not going to go over anything else. So does anybody have any questions about stratospheric chemistry? That's the end of the stratosphere as far as your degree is concerned, I think. You don't need to learn anything more about the stratosphere. But do you have any questions? Anything that you're not certain about?
I got a question on the chemistry. I want to know why should we care about the South Pole?
Why should we care about the South Pole ozone hole? Do any people live in the South Pole? Some scientists. So we don't care about a few scientists in the South Pole. 20 million square kilometres is not just over the South Pole. Okay? So if you look at the vortex, if you look at the size of that area there, do any people live anywhere underneath that? Sorry? Yeah, I suppose. It's not quite limited. You get some significant depletion over Australasia. Australia has a is there just in the area where you allow enough ultraviolet to reach the surface that doesn't, such that it's not absorbed by the ozone in the stratosphere. And there are huge, you can plot a line showing the increase in the skin cancers in Australia and the reduction of ozone in the South Pole, because it's in the area where you have significant. Where's? It's really rubbish. This. Have we got any other? No, there's nothing on here. But Australia is roughly, it's in this green area. Yep. So it's in the green latitudes. And look, that's Africa there. Yep.
South America.
Is this South America? It is South America, you're right. Sorry. South America. So Chile, Argentina. Yeah. So, okay, there's a few people in South America that might not like it. There's a few people in Australia that might not like it. So if we don't care about South Americans or Australians, I don't know. But not only that, what are we saying about the ozone? Is there any, if CFCs continued, which could continue to be emitted, we saw that there was a trend from the 1960s to the 1980s over Switzerland. Yep. So it's not this polar stratospheric cloud particularity, the particularity of the chemistry showed that you got these huge ozone depletion events because of that sort of chemistry over the South Pole and in large areas over the Southern Hemisphere. But also the chemistry, that was just indicative of the various cycles. Because you've got the Hox, Nox and the clock cycles all acting, and these are all increasing with anthropogenic activity, then there was an indication that we've got global reduction in the ozone, although it was much greater over the South Pole. Okay? So I don't know whether we care. Do we care? Do we like our friends in South America and Australia? But generally, it's a signpost to show that we're affecting the chemistry in the stratosphere, which we don't know how much, whether there are thresholds that could lead to more ozone destruction elsewhere on the planet. Good question, though. So maybe I'll ask that in another exam sometime. So yeah, your cohort next year or the year after, I'll set that as a question for them. Okay? Any other questions? Anything else? Intrigued by anything else? Should we move down to the troposphere then? We'll just have an introduction of moving down to the troposphere. Next week, I will not be here. Next week I'm in Budapest. But I will upload on Blackboard a whole series of questions for the aerosol side and for the gas side. Okay? And I expect you to spend some time going through those questions, and then we'll have a drop-in day, and perhaps I'll go through some of them the week after. But we've got a lot more material to cover, so what I'll do is just submit questions to Blackboard for next week. Are you okay with that? Yeah? I'll just give you a bunch of examples. Right, so that's enough. Enough stratosphere. We're bored in the stratosphere. Yeah, it's all this. It's all this.
Okay? Board, not doing any more with that. Not doing anything more than that. Right. So what we're going to do now is consider what happens in the lower 10 kilometres of the atmosphere. And mostly, we'll be concentrating on what happens in the lowest kilometre. Why are we interested in what's happening in the lowest kilometre? Because we live here. More importantly, because we breathe here. Yeah? We live here and breathe here. We're interested in what goes on up here because we expose our skin here. We're interested in what goes on here in the lowest kilometre or so because we breathe the air. So this is where most of the chemistry happens. Why does most of the chemistry happen in the troposphere? Really simple question. Simple answer. Why does most chemistry happen in the troposphere? Because most of the molecules are in the troposphere. Okay? What is most of the chemistry? Well, a big part of the chemistry is photochemistry, and most of the high energy photons are up in the top of the atmosphere. But the other part of the chemistry is gas kinetic chemistry. It's where all the collisions happen. Okay? You've got higher pressure, you've got more molecules, you've got an elevated temperature, and so most of the chemistry happens in the troposphere. What else happens in the troposphere? Well, the air can speak to the surface. So the land atmosphere interactions and the ocean atmosphere interactions all happen in the lowest part. So most of the chemistry happens and most of the loss processes happen in the lower atmosphere. So we remember photostationary state. So keep remembering this, because it's important. Drives the chemistry. Drives a lot of the chemistry in the troposphere. So NO2 photolyses, releases NO, molecular oxygen and atomic oxygen release your ozone. Your ozone then reacts with your NO to reproduce your NO2. And all of these happen in a very fast photostationary state. We've already shown in this example here how you can calculate the loss rate of each of the species as the production rate minus, the rate of change as the production rate minus the loss rate. So from these equations you can see that the dNO2 by dt equals the production rate of NO2 minus the loss rate of NO2 just from photolysis. And so dNO2 by dt is 0. And you can come up with, because all of these are in steady state, you can come up with this whole range of relationships, steady state relationships. Just as you did for that example in the stratosphere. So it's just, most of the chemistry you have to deal with can be summed up in this sort of a description. Not very complex as a concept, but it can be applied to very many complex systems. So you can derive these same photostationary state relationships from the rate of change of NO. Because it's the coupled system, they're all in steady state, all of these relationships can be derived from each of the others. So it doesn't matter where you start from. So, what drives the cycles of tropospheric photochemistry? Which of these species has the shortest lifetime?
Which of these photolyzing species has the shortest lifetime? The nitrate radical, which is formed from NO2 plus ozone, what does that tell you? Here. The nitrate radical plus a photon gives NO or NO2. What's the lifetime of this transition in the atmosphere? How long will NO3 live with respect to this transition?
10 seconds. 100 seconds.
Okay, so this is 4 times 10 to the minus 2. So it's about a 25th, about 25 seconds. Okay? 4 100ths is the rate, 4 100ths, so 1 over 4 100ths. And here it's about 10 seconds. So it's got a lifetime with respect to the first transition of about 25 seconds, and a lifetime with respect to the second transition of about 10 seconds. So it means its lifetime overall is less than 10 seconds, so it's about 7 or 8 seconds on average in the troposphere. So how much NO3 will we have? In the daytime, none. Almost none. It's produced from this reaction, but it's photolysed in a few seconds. This is a modestly quick reaction. This, photolysis, is a very quick loss. So production minus loss, very small production, very high loss, means that you have none. What happens at night? The NO3 concentration goes up. So what's the most important oxidant in the troposphere? Do we know? OH is formed from ozone plus a photon, and of course it goes through O singlet D plus water vapour. Yeah, but yields OH. This happens when there's a photon. Ozone itself is an oxidant. And NO3 is an oxidant. NO3 doesn't exist during the daytime because it photolyzes very quickly. OH doesn't exist at night time very much because there's no light to form it. The ozone's got a longer lifetime. If you look here, the ozone photolysis, thousands of seconds, so several hours. So it's got a much longer lifetime with respect to photolysis, so one of its main loss routes of odd oxygen. And so that can last into the night time. So ozone is formed during the daytime and persists into the night time. OH is only formed in the daytime. It's got a very short lifetime, so it only exists in the daytime. NO3 is formed at night time, but it's got a very short lifetime with respect to photolysis, so it only exists at night time. So your daytime, nighttime, OH, ozone, NO3. OH happens in the daytime, but not at night. Ozone's there daytime and nighttime. NO3 is not there in the daytime, but is there at night. So in the day, you've got OH and ozone, and at night, you've got ozone and NO3. because of the different photochemical production and loss lifetimes. And you can see here that there are lots and lots of different species that we're interested in the troposphere. Each of these species yields another player that is of importance in tropospheric chemistry. So we already know about the NOx photostationary state. NO2 photolyzes to give you NO plus atomic oxygen at somewhere less than 420 nanometers. Do we have light at 420 nanometers in the troposphere? What colour is 420 nanometers? Sorry? Yeah, it's kind of bluish. It's roughly that blue. Can you see that? Yeah? Do we have blue light in the troposphere? Yeah. NO2 is going to photolyse in the troposphere. Okay? So NO2 will photolyse in the troposphere. And that's the only way of producing ozone in the troposphere. Troposphere. That's wrong, isn't it? Okay. It's the only way of producing ozone in the troposphere. Can you think of any other way to produce ozone in the troposphere? Lightning. How much how much ozone do you think would be produced from lightning in the troposphere? And do you produce ozone directly from lightning? You produce NOx, which produces ozone in photostationary state. Okay? You don't actually directly produce it. I suppose you might from the corona. If you're actually in the corona, you might get corona discharge to produce ozone. And photocopiers. And laser printers. Okay, so that's not completely true. But I would say 99.999% of ozone is produced from NO2 plus a photon. So the dNO2 by dt can be calculated here from the photolysis rate and this reaction rate. So can you all calculate this? Can you all carry out this calculation? Is it straightforward to you? If you've got 30 ppb of NO, 30 ppb of ozone, a ppb of NO, a ppb of NO2, you have a characteristic time from this reaction of about 100 seconds. So if this has got an E-folding time of about 100 seconds, and if these are the only reactions happening, then the ozone is about 23 parts per billion of these sorts of concentrations. So this might be the background tropospheric concentration. It's not an urban concentration, and you don't have the same ratio of NO to NO2 in the urban environment either. But you'd have about 23 parts per billion of ozone at a part per billion of this. What about ozone removal? Well, ozone photolyses to ground state oxygen and hot oxygen. And the recombination
of the atomic and molecular oxygen gives you ozone. Most of this is collisionally deactivated back to this, and some of the O singlet D forms hydroxyl radicals.
So forms your daytime dominant oxidants.
So 2 hydroxyl radicals are formed here, and so 0.2 OH are formed for each ozone molecule, because only 10% of the O singlet D reacts with water vapour. So about 0.2 OH for each ozone molecule that goes down this channel. And you can relate the amount of OH. So the OH here goes up and down. You can see at night time there's no OH, daytime there's OH. This is the JO singlet D, so that's your photolysis rates, that's your photolysis rates, etc. This was the latitude, the longitude at which it was measured, and this is the ozone concentration.
So we can measure. So how might you measure the hydroxyl radical? You don't need to know this, but it only lives for about a second or two. And it's a very, very reactive species. But what it does do is it fluoresces if you hit it with light of the right wavelength. So you measure it by on-resonance measurement of the laser-induced fluorescence at 208 nanometers. Don't need to know that, but that's what these measurements were made with.
On-resonance fluorescence measurements.
Of course you can. Don't know where. Right, cheers.
I've lost it forever, sorry.
Quite frequently do this. Oh. Cheers.
Thank you.
Good night.
Okay, so shall we? Right. This presentation is on Blackboard.
We now start to talk about tropospheric oxidants. We talk about the hydroxyl radical, the different radical cycles, etc., daytime, nighttime oxidants. Try and familiarise yourself with it for 3 weeks' time. Next week I'm not here, the week after is aerosol, the week after that is this. So give this presentation a read. By the time you've finished this presentation and we've had the lecture in 3 weeks' time, that's the end of the chemistry part of your syllabus. Okay, so give this a read before next week and you should be able then to address all of the questions that I'll be uploading onto Blackboard. Stratospheric and tropospheric. Okay? So this is the last lecture, but it won't be completed until 3 weeks' time. Read it and you'll be able to do all the questions. Everyone comfortable with that? I'll see you in 2 weeks. You good? Not broken, is it?
Yes.
It's okay. Okay. As long as it's not broken.
Yeah.
Oh, yeah. Okay. Thanks very much.